Stress corrosion cracking, SCC, direct assessment methodology techniques for evaluating corrosion-induced metal failures. Stress corrosion cracking, SCC, direct assessment methodology, introduction to stress corrosion cracking, types of stress corrosion cracking. This presentation provides a professional overview of the stress corrosion cracking direct assessment, SCCDA, methodology as defined in NACE SP0204. SCCDA is a structured, integrity management process developed to identify, evaluate, and mitigate the threat of stress corrosion cracking in buried or submerged pipelines. The methodology is primarily intended for pipelines that are not currently inspected using inline inspection tools or where ILI data requires supplementation. SCCDA emphasizes a systematic, step-by-step approach that integrates engineering judgment, historical data, field inspection results, and risk-based decision-making. The presentation is designed to support engineers, integrity specialists, and asset managers by explaining the purpose of SCCDA, its role within a broader pipeline integrity management program, and how it supports regulatory compliance and safe operation. Particular attention is given to how SCCDA aligns with preventive maintenance philosophies and lifecycle asset management. By understanding SCCDA, organizations can proactively manage SCC threats, reduce the likelihood of sudden failures, and prioritize integrity actions based on susceptibility and consequence. Stress corrosion cracking is a form of environmentally assisted cracking that occurs due to the combined action of tensile stress, a susceptible material, and a specific corrosive environment. In pipeline systems, SCC often develops on the external surface of carbon steel pipelines and can progress with little or no metal loss, making it difficult to detect using conventional corrosion monitoring techniques. The tensile stress component may arise from residual stresses from manufacturing, welding, or cold bending, as well as operational stresses from internal pressure. The environmental component typically involves specific soil chemistries, moisture conditions, and electrochemical potentials. SCC is particularly dangerous because cracks can grow over time and coalesce, potentially leading to sudden rupture without significant warning. Understanding the fundamental mechanisms of SCC is essential for appreciating why targeted assessment methodologies such as SCCDA are necessary and why reliance on general corrosion indicators alone is insufficient. Stress corrosion cracking in pipelines is commonly categorized into high pH SCC and near neutral pH SCC, each with distinct environmental and morphological characteristics. High pH SCC typically occurs in alkaline environments associated with concentrated carbonate bicarbonate solutions and often presents as intergranular cracking. Near neutral pH SCC, by contrast, develops in environments closer to natural soil pH and is generally transgranular in nature. These two forms of SCC differ in terms of crack appearance, growth rates, and associated electrochemical conditions. Understanding the type of SCC present is critical for selecting appropriate indirect inspection tools, excavation strategies, and mitigation measures. SCCDA recognizes these differences and requires practitioners to consider environmental data, coating conditions, and operating history to distinguish between SCC mechanisms and accurately assess susceptibility. Overview of SCC Direct Assessment, SCCDA, SCCDA Process Steps. SCC Direct Assessment is a formalized integrity assessment process specifically designed to address the unique characteristics of stress corrosion cracking. Unlike general corrosion direct assessment, SCCDA focuses on identifying pipeline segments that are susceptible to SCC rather than attempting to find all existing cracks. The methodology integrates multiple data sources, including design information, operating conditions, environmental factors, and inspection results, to systematically reduce uncertainty. SCCDA is particularly valuable for pipelines where inline inspection tools are not feasible due to diameter, geometry, or operational constraints. It is also used to complement ILI by providing contextual information about SCC drivers and confirming inspection findings through field validation. The ultimate goal of SCCDA is to enable informed decision-making regarding excavation, repair, mitigation, and reassessment intervals. The SCCDA methodology is structured around four key process steps: pre-assessment, indirect inspection, direct examination, and post-assessment. Each step builds upon the previous one and is designed to progressively refine the understanding of SCC threat. Pre-assessment involves gathering and reviewing historical and operational data to identify potentially susceptible pipeline segments. Indirect inspection applies above-ground survey techniques to prioritize locations for excavation. Direct examination confirms the presence and severity of SCC through physical inspection and non-destructive testing. Finally, post-assessment integrates all findings to determine mitigation actions and establish reassessment intervals. This structured approach ensures consistency, traceability, and defensibility of integrity decisions, which is especially important for regulatory compliance and risk management. Detailed SCCDA implementation steps: pre-assessment, indirect inspection, direct examination, post-assessment. The pre-assessment step is the foundation of the SCCDA process and focuses on collecting, reviewing, and analyzing available data to identify SCC-susceptible segments. Key data sources include pipeline design and construction records, material properties, coating type and condition, operating pressure and temperature history, cathodic protection performance, and environmental characteristics. The objective is to determine whether SCC is a credible threat and, if so, where it is most likely to occur. This step relies heavily on engineering judgment and data quality, as incomplete or inaccurate information can lead to incorrect prioritization. A well-executed pre-assessment allows operators to focus resources on the most critical areas and improves the effectiveness of subsequent inspection activities. Indirect inspection involves the use of above-ground survey techniques to identify and prioritize locations that may be experiencing conditions conducive to SCC. Common tools include close interval potential surveys (CIS), direct current voltage gradient (DCVG), and alternating current voltage gradient (ACVG) surveys. These techniques help identify coating defects, cathodic protection anomalies, and areas of potential shielding. While indirect inspection methods do not detect SCC directly, they provide valuable indicators that help rank excavation sites. The effectiveness of this step depends on proper survey execution, data interpretation, and integration with pre-assessment findings. Indirect inspection serves as a critical link between data analysis and physical verification. Direct examination is the step where selected pipeline locations are excavated to confirm the presence, type, and severity of SCC. This process includes coating removal, visual inspection, and the application of appropriate non-destructive testing methods such as ultrasonic testing, magnetic particle inspection, or dye-penetrant testing. The objective is to characterize crack morphology, depth, and extent, and to determine whether cracks are active or dormant. Direct examination provides the ground truth necessary to validate assumptions made during earlier steps. The findings from this step are critical for determining immediate repair needs and for refining the overall understanding of SCC susceptibility along the pipeline. Post-assessment integrates the results of pre-assessment, indirect inspection, and direct examination to support final integrity decisions. This step involves evaluating the effectiveness of the SCCDA process, determining appropriate mitigation measures, and establishing reassessment intervals. Engineering assessments are performed to evaluate crack severity relative to acceptance criteria and remaining strength models. The post-assessment step also identifies opportunities to improve data quality and inspection practices for future cycles. By systematically documenting findings and decisions, this step ensures that SCCDA outcomes are traceable, auditable, and aligned with the operator's integrity management objectives. Mitigation measures, advantages of SCCDA, limitations of SCCDA. Conclusion. Mitigation measures following SCCDA are selected based on the severity and extent of SCC, as well as the underlying contributing factors. Common mitigation actions include coating repair or replacement, cathodic protection optimization, stress reduction through pressure management, and removal or repair of cracked pipe sections. In some cases, operational changes or enhanced monitoring may be implemented to manage residual risk. Effective mitigation not only addresses existing damage but also reduces the likelihood of future SCC initiation and growth. The selection of mitigation measures should consider technical effectiveness, constructability, cost, and long-term sustainability. SCCDA offers several advantages as part of a comprehensive pipeline integrity management strategy. It provides a targeted, risk-based approach that focuses inspection and maintenance resources where they are most needed. SCCDA is particularly valuable for pipelines that cannot be inspected using inline tools and for validating or supplementing ILI results. By integrating multiple data sources and inspection methods, SCCDA improves understanding of SCC threats and supports proactive decision-making. The methodology also promotes consistency and defensibility in integrity assessments, which is beneficial for regulatory compliance and stakeholder confidence. Despite its benefits, SCCDA has inherent limitations that must be recognized. The methodology is highly dependent on the quality and completeness of available data, as well as the expertise of the personnel performing the assessment. SCCDA does not guarantee detection of all SCC and should not be viewed as a full substitute for inline inspection where ILI is feasible and effective. Indirect inspection techniques provide indicators rather than direct evidence of cracking, which introduces uncertainty. Understanding these limitations is essential for setting realistic expectations and for integrating SCCDA appropriately within a broader integrity management framework. Stress corrosion cracking direct assessment is a critical methodology for managing SCC threats in pipeline systems, particularly for aging infrastructure and non-piggable lines. By following the structured process defined in NACE SP 0204-2015, operators can systematically identify susceptible segments, verify damage through targeted excavations, and implement effective mitigation measures. SCCDA supports a proactive, risk-based approach to integrity management that enhances safety, reliability, and regulatory compliance. When properly implemented and integrated with other integrity tools, SCCDA plays a vital role in extending asset life and preventing catastrophic failures.